Okay, I'm Roger. You heard about me before, so I'll leave the introduction. So, I forgot to mention earlier, probably something that will make you look at me in a new light. I contract for the United States government to build anonymity technology for them and deploy it. They don't think of it as anonymity technology, though we use that term. They think of it as security technology. They need these technologies so that they can research people they're interested in, so that they can have anonymous tip lines, so that they can buy things from people without other countries figuring out what they're buying, how much they're buying, where it's going, that sort of thing. So it's not just individuals who care about this sort of thing. Governments are paying for it right now. And we'll get to that in a little bit later. So basically what I have built here is a low latency anonymity system. It's designed for web browsing or SSH or instant messaging. There are a variety of different things that you can use over it. It basically transports whatever application you want. So there are a bunch of nodes out there. There are 25 or 30 servers around the world, many in the US, one in Canada, some in Europe. It's available under free software license. You can get it right now. You can use it, change it, sell it, do whatever you want to. It's no longer covered by the patents that used to cover onion routing designs because we improved the technology, so it happens that the patents no longer cover it. We use it basically when you install the client on your system, it looks just like a SOX proxy. You heard from Enki earlier about should we make it visible, should we make it hidden. In our case, it's a proxy that runs in the background. You can point your Mozilla at it or whatever, and it simply tunnels the connection through it. We've got working code. It's reasonably small, 20,000 lines of C. We have a design document which will be presented at Usenix Security in August. We have a byte-level specification. The JAP folks actually re-implemented Tor based on our specification, so now there are two independent implementations, which should give you some confidence in the fact that the spec actually reflects what the code does. It's packaged in Debian. If you are a Debian person, run apt-get install Tor and you'll have it. It's also in FreeBSD ports and so on. It works on all sorts of operating systems. It's user space. You don't have to install a kernel change or be root or anything. So onion routing itself is an overlay network. Enki talked about overlay networks before. So you've got the internet, and then you have a bunch of other servers on top of that, and you route between them. So basically, users build virtual circuits and connect. So the user chooses maybe 3 or 4 servers around the world, and they build a circuit through that, and then they connect, and their connections come out of the other end. So for instance, if you're watching what I'm doing, in reality I'm maybe going to indiemedia.org, but you see me connecting to some server in the Netherlands and it's encrypted. And indiemedia.org sees somebody from Canada doing a connection, and I happen to be sitting in a room in Berlin. So that's the basic idea. And there is a layer of encryption at each hop which foils some level of traffic analysis. Okay, so let's step back a second from the technology issues. Anonymity is a network effect. You can't be anonymous by yourself. If you're using PGP, Alice and Bob want to communicate, and they want it to be encrypted. They want confidentiality. So if the two of them figure it out and they get the usability issues right, Alice can send something encrypted to Bob, and that will work. If Alice and Bob get together and they say to themselves, we want to anonymously communicate with each other, that's not going to work. You need a whole lot of other people that you're blending with in the same crowd so that you can use it. So anonymity is a bit more complex than encryption issues. Also, usability affects security. Usability in the case of PGP means that either Alice screws up or she doesn't. But whether Alice screws up doesn't affect somebody else's security. Whereas in an anonymity system like this, if I screw up, then I'm not blending with you as well as I was before. So we need to build technology that lots of people can use so that we can get security in the system. The more users we have, the better off we are. So a distributed trust system, we heard earlier a little bit about what happens when you set up a single node and you trust the guy and you hope that his government is a reasonable enough government that they won't let the Church of Scientology or some other bullying organization show up and figure out what's going on. So you can't simply have one entity running the anonymity system, because that entity is open to corruption or it's open to other larger organizations attacking them. Even if it's a large corporation or a government, the United States government can't simply run an anonymity system for everybody and then use it themselves only, because then every time a connection came from it, people would say, oh, it's another CIA agent looking at my website, if those are the only people using the network. So you need to have other people using the network so that they blend together. And along those same lines, you guys don't want to use an anonymity system run entirely by the US CIA, because you don't want to trust that they have your best interests in mind. So you want to run a part of the infrastructure, and people in Austria do, and people in Canada do, and so on. And you need a decentralized infrastructure so that everybody can trust that they're getting the security they want. Okay, so the threat model that Tor aims for is a little bit stronger than the single hop system. Basically, Alice is trying to talk to Bob. We want to protect against somebody who's watching Alice, who's wondering where she's going to, what websites she's hitting. We want to protect against a curious website. Indie media is saying, gosh, I wonder who are the advocates today? Should we be paying attention to these people or those people? Or maybe the government is logging who's looking at indie media and they can track down various dissidents. We also want to protect against some curious nodes in the middle, and I'll talk a little bit about what I mean by some in a bit. Analyzing low latency systems is a bit hard. So we're TCP only. We don't do UDP or other things like that. So you can't play Quake over Tor, but you can web browse over Tor. So there are some limitations. But on the other hand, because of that, we're user space. You don't have to be root on your system. We're quite portable. We're not as strong as the high latency systems. You heard about remailers earlier, where you can take 4 or 5 hours to get your email from one place to another, and that lets you mix with lots of other emails. In this case, users want to get their web page soon after they click on the thing, so you can't actually have time to mix with other things. We're not peer-to-peer. Right now, there are a group of 25 or 30 servers out there, and those are the servers, and you are the clients, and it's a client-server system, even though there's lots of redundancy. We'd like to make it scale to the point that we can have thousands of servers, but that's a hard design problem, which we're working on. We don't actually care what you do over the network. If you go to Amazon and you give them your name and your credit card, then you're no longer anonymous, and that's not our problem. You have to decide what actual data you're going to transport. All we provide is location anonymity. We can hide your IP from where you're going. What you actually send to them is your problem. Also, we're not unobservable. We're not trying to provide steganography or something like that. The adversary watches you send an encrypted connection to some machine in the Netherlands or something. He doesn't know where you're going, but he knows you're doing it. So we're not trying to protect against that also. Okay, so we don't do any mixing or padding or traffic shaping. A lot of people who work on these systems say, oh, we'll just send a lot of traffic on top and then people will get confused. If you're using a low latency system like this, there are attacks where the adversary looks at the beginning and the end. And if he can see both you and the website you're going to, then he can correlate that some packets come out this end and they arrive here, and then some packets return and then they arrive here. There are really good attacks that let the adversary win if he can see both the beginning and the end. So based on that, we simplified everything. We don't do any mixing. We don't try to mess with throwing traffic around to try to confuse people. We just aim for usability so that the system can actually work. So there's another technology that works in this also. So I've been talking about Alice retaining her anonymity as she goes to a website. But we also have a system where the website itself can allow people to get to it without revealing its location. The basic idea for this is that both people onion route out and they get connected together, but this Alice doesn't know where Bob is and Bob doesn't know where Alice is, yet Alice can get to the website. So you can offer, for instance, an Apache server or an SSH server or an IRC server without revealing its IP. So this is of interest for censorship resistance because people don't know where the website is. It's also of interest to governments for denial of service resistance, because if they figure out where the website is that you're issuing your military orders from, then they send a bomber and they blow up the city and your website's gone. But if they don't know where to send the bomber... So it's not just individuals who care about this sort of thing. There are also companies and governments that look at it from a robustness perspective for what they need to do. So we have directory servers. If you start out, the first question lots of people ask is, okay, I've got my software running on my client. How does it know what the servers are out there? So there are a group of redundant systems out there that keep track of which servers are in the network, what their keys are right now, what IPs they're at right now, and so on. And this is a bottleneck in the system, and it has to be a bottleneck from the human perspective, because otherwise your adversary would show up with 35,000 servers, and so there would be 35,000 bad servers and the 25 good servers that we have, and your chances of picking a good person either at the beginning or the end of your path would be pretty much zero. So we need some mechanism to limit the bad guys who show up so that we know that each server is being run actually by different people. Because if they're all being run by the same person, then you don't get the security that you think you're getting from the system. We've got variable exit policies. The JAP system, which I'll talk a little bit about at the end, basically has... So the onion routing system, the Tor system, is free route. The user picks her path. The user software actually does it automatically, but the user can have some influence on it. But basically you can pick any route through the network. Any of these servers can be used in any order. There are some other designs where they have, these are the 4 servers, you use them in this order, and that's that. And the idea is that people all mix together, and then they come out together, so it's not clear based on who went in, who comes out. But they have to actually have one server out there that all the traffic exits from. And they have a big team of lawyers which deal with whatever comes out and whether people are unhappy about what comes out. But the onion routing approach is, there are lots of people out there in lots of different jurisdictions. Plenty of jurisdictions don't care what comes out of their onion router. Why don't we let volunteers set up servers, and hopefully everything will work out. And so far it has worked out. We've got no abuse complaints so far from the Tor network. It's been running since October. And we'll see how that works out later. But each operator can decide what he wants to allow to exit from the network at his hop. So plenty of people sign up and say, I want to contribute bandwidth, but I don't want to be the guy who gets the mails. I don't want to be the guy who gets the complaints. So you can set yourself up as a middleman server, and that way you don't allow anything to exit at your server, but people can enter at your server and can hop through it on their way to an exit server. So there are lots of different ways you can configure your node depending on whether you want to provide bandwidth or lawyers or what your capabilities are. Okay, how's my time?
3 more minutes.
3 more minutes. Okay. So there are some technical details which I'm going to skip over and go to a question.
Okay, I give you 5.
And I'd be happy to talk to you more about the actual details of how we improved the system compared to other onion routing systems. But talk to me afterwards. So one question here. We've got a lot of different anonymity systems out here. And plenty of people, every time they build them, they say, I have a perfect system. If you use this, you are guaranteed to be safe. And pretty much everybody who builds one of these systems says that. And they can't all be right, because they're all building different sorts of systems, and they all have different sorts of adversaries in mind. So I have one way of analyzing these systems and comparing them here. So assume you've got n nodes out there in the system. We've got 25. Assume the adversary owns C of these n nodes. I don't know how many C is, but maybe it's a couple, maybe it's half of them. It depends on who the adversary is you have in mind. Probably large echelon-style government consortiums can watch quite a few of the nodes in the network. So imagine he owns C of the n nodes, and imagine he can choose which ones he can watch or compromise or control. So what's the chance for a random Alice talking to a random Bob that the adversary can successfully link Alice to Bob? That's the question we want to ask. And in the case of the Freedom Network and the Tor network, the adversary wins if he owns the first node and the last node. So there's a C over n chance of picking a bad first node, and a C over n chance of picking a bad last node. So if you multiply those, you've got C squared over n squared. So that's the protection that Tor tries to provide. So there are some other highly scalable systems like Peekabooty and 6.4 and Freenet, and you've heard a lot about those perhaps. And the security that they offer is you pick the first node, and then the first node picks the next node and the next node and so on. So if I pick a bad first node, I'm screwed, because the adversary owns it, and he dictates where I go from there. He says, oh, I've randomly decided to pick this one. I've randomly decided to pick this one, and you're going to exit over there. So there's a C over N security property from these networks, because if you pick a good first node, you're okay. They don't know where you're coming from. If you pick a bad first node, then you're screwed. So that's we'd like to be able to scale Tor to the point that we can cover the globe with it, but we don't know how to do it and maintain the C squared over N squared security properties. Any way we can think of so far brings it back to C over N. And we've got the JAP system, which is running at Dresden, also in comparison here. So it's just 4 nodes in a row. And if the adversary watches the first one and the last one, then they can correlate any traffic that's going through the network. They can say, oh, 500 bytes came in here and 500 bytes went over to that website. I bet those are the same guys. And JAP is even worse than that, because all of those 4 servers are pretty much in the same room. And so if you happen to show up with the good enough warrant, and
It's not true.
recently they've added one in NYU in New York, and there are a number around Germany now.
There is one in Kiel. There is one in Humboldt University.
In Germany,
In
and Germany,
Germany.
and Germany? Okay.
Yeah, they're mostly based in Germany, but
Okay.
they're in different locations.
Okay, but they're under pretty much one jurisdiction. And the JAP people actually had a problem with that recently when the German government showed up and said, we have a warrant to find out who this guy is. And it seems that all of those computers are in the same jurisdiction, which is ours. So could you please explain to us who is connecting to this website? And they were forced to do that.
That's right, but you can
Yes.
use the other cascade that's going over New York, for example, then.
So it's good that they have 2 jurisdictions now. I think that's better than 1. But I still think that there are some designs which allow you to take advantage of more jurisdictions, of as many jurisdictions as you have volunteers around. So there are many other ways of analyzing these systems, and in some of them, JAP is quite comparable to Tor in security. But from my perspective, where I'm thinking of a reasonably global adversary who can look at a lot of different places and can decide which servers he wants to monitor, I want to get some idea of how much protection I get from that adversary. And for comparison, we have the anonymizer up here. It's a single hop proxy. It runs in San Diego, California, and it has 50,000 users or something, paying users. But on the other hand, it's a single hop proxy. So if the adversary happens to get a court order or something to watch that, then they see people coming in and going out, and they're able to figure out who is who. Okay, so future work, we'd like to make it scale, and we'd like to try to figure out how to do that while retaining security. And from Robert's perspective, it would be nice if we could design a Tor system which was usable not just in the modern countries that we're using it in now, but also in other countries. And it's really hard to build a system that works in that sort of environment. A lot of the problems are in education rather than just the technology. Okay, so we have working code. I've told you about that. Talk to me afterwards. Or there's a workshop right after this where I believe we are going to pit my software against an eavesdropper who will try to tell me where I am going to. And we'll see if the eavesdropper succeeds or if I succeed. Freehaven.net/Tor is where you can get the software. Also, the Privacy Enhancing Technologies workshop will be at the end of May in Dubrovnik, Croatia. And petworkshop.org is where you want to go to learn more about that or chat with me afterwards. Thank you.
Well, the step over to the next subject is actually pretty difficult now, but I will try to bridge this gap. In his talk and also in the discussion that was preceding it, we have been talking about 2 different threats. One is the state, which can survey traffic, and where we have this trouble of perhaps one legislation. The second is the commercial surveillance by companies. Now, often we refer to, especially when it comes to commercial surveillance, we refer to click streams and we refer to clickstream analysis. And we know that companies, not only on proprietary web servers, look at how people buy and move through online stores, but we also know that some companies track the traffic that's being generated on several web servers, like, for example, ad companies. And what you can think about is something like a map that shows how people move around the virtual, the online world, the online space. Now, the online world is very important, and certainly to the audience in here. But something very crucial is happening right now, because the electronic world is actually being integrated into the physical world by the help of sensor technology and by the help of intelligent tags. This in the future, as intelligent chips that are integrated in everyday objects like clothes, for example. This will allow companies as well as governments to survey people not only in the online world but also in the offline world. Just figure that you have an RFID chip in your shoe or in your clothes and you are moving around a city. There is considerable interest, for example, for companies to generate profiles of how people move through cities. You can rent out your space much more expensively if you know that a lot of people are passing by. If you even know that they're rich people because they wear expensive clothes, they are wearing expensive clothes, that makes your rent even higher. For governments, there is a similar interest. Imagine that you would not only you don't use video surveillance necessarily anymore, but you're reading out the identity card of people, and you can immediately look into a database when by chance a child has been kidnapped from a public playing ground, and you just look into what personal IDs have been passing by. So these are some scenarios where perhaps we can talk about not the click stream, but this step stream, I have tried to call this. And Rena Tangens is now going to talk about this issue, the issue around RFID technology.